the location of new MEMS gravimeters on a summit road and Forestaller road here on the west of Etna, such that we can image the sources of mass change at Etna in an optimal way. So with optimization, exactly as I said, we mean minimizing the uncertainties associated with these sources of magma, or in other words, we wanted to gain the maximum information about these sources. For this purpose, we have developed analytical and numerical optimization methods that I will explain later. We have also developed a method to find the minimum number of gravimeters necessary for this purpose. And in the end, I'll show you the application of the method to Mount Etna. So a source of mass change, a point mass, can represent any new magma that is intruded into the edifice. And a gravimeter in this figure is represented by this triangle. A gravimeter can measure the vertical component of gravity change associated with any point mass. This observation can be better represented by equimass contours here in panel B of the figure. If we assume that we are observing 20 microjoule of gravimeter, this can be caused by a point mass right below the gravimeter. The amount of mass is shown here. If the point mass moves on this equimass contour line, the observed gravity change does not change. So for 20 microjoule, we have 20 microjoule of gravity change. We can assume there are infinitely many equimass contour lines corresponding to different amount of mass, different point masses. So what we want to do in this problem is to infer the parameters of point masses, new masses intruded into the edifice of a volcano, for instance. And each point mass has 4 parameters. 3 are the coordinates of the point mass, and the 4th parameter is the amount of mass. If you want to constrain these parameters by using gravimeters only, we need at least 4 gravimeters because we have 4 unknowns. And the problem can be visualized this way. For each gravimeter, we basically consider the equimass contour lines and find the set of lines that exactly intersect at the same point. This way, the point mass is completely constrained. But as we know, the observations have errors, and therefore, rather than having exact equimass contour lines like the previous panel, we get stripes. And the area that all of these stripes are overlapping represents the uncertainty associated with the constrained point mass. And this uncertainty is a function of the gravimeter location. As you can see here in this panel, the area of the overlap is much smaller than the previous figure, than the previous configuration of the gravimeters. So basically, by optimization of a network of gravimeters, what we mean is to minimize the area, or better to say, the volume of uncertainties. So if we minimize the area of the volume, the uncertainty volume, we are actually maximizing the information content that we can gain from this network. By the uncertainty volume, what I mean is, in mathematical terms, is the determinant of the covariance matrix associated with the point mass parameters. So what I want to point out here is that the uncertainty volume or the information content corresponding to a point mass and a given network of gravimeters can be calculated. So we first address this optimization problem using an analytical method. In this problem, I consider a 1D network of gravimeters, which are these three triangles along the x-axis. So the point mass in this problem basically has three parameters, because we are assuming that the parameters of interest are the location of the source along the x-axis and the depth of the source and the amount of point mass. So solving the problem analytically, we can see that the optimal network has such configuration. The one gravimeter is right above the source and the other two at these given distances from the center. The second optimal solution that we derived is shows a 2D network. In this case, we have the top view, and the point mass is right below the origin. As you can see, the optimal configuration again has one gravimeter on top of the source, and three other gravimeters form an equilateral triangle. So in the next step, we used the genetic algorithm to develop a numerical optimization tool. And as a first step, we use the analytical solutions to benchmark this numerical scheme. So I have to say that this numerical scheme is very fast and is developed in terms of a guided search based on the genetic algorithms, as I said, and it can quickly solve the problem for different kind of problems with different setups. In the first case, we considered a 1D network. We assume that all the gravimeters are located on the x-axis. The source is located at a depth of 6 kilometers, and as you can see, it is represented by the green cross. So these three lines represent the solution from represent the 1D analytical solution, and as we can see, the numerical optimization gives us a solution which is in very good agreement with the analytical solution. In the second test, we use the 2D analytical solution. Again, in this case, we have the source represented by this green cross at the depth of 6 kilometers. And the triangles represent the solution from the numerical scheme. And this circle represents all the points at a certain distance from the center. And this distance is given by the analytical solution. We refer to this distance as the characteristic distance, and also to the circle we can refer as the characteristic circle, because it represents the analytical solution associated with this particular point mass. Then we do another test. In this case, we use 20 gravimeters, and we are interested in finding the optimal configuration. So we don't have an analytical solution for this one, but it is interesting to see that all of these new gravimeters also fall either on the top of the source or on the characteristic circle. But as it can be seen, here we have several clusters of gravimeters. And by cluster, I mean gravimeters which are co-located. We see that if we introduce some empirical correlation between these gravimeters, we can avoid this issue of clustering of gravimeters. But again, it is interesting to see that still we have all the gravimeters on the characteristic circle, and some of them circled around the source on its top, right above the source. So this validates the numerical solution that we have developed. But these examples showed only one, considered only one point mass. What should we do in case of multiple target point masses? So again, we do a test. In this case, we have two point masses at the depth of 6 kilometers and 3 kilometers. And in this other panel, panel B, we have 3 point masses located at different depth and locations. So these two sources here, up here, with their characteristic circle, they are both located at a depth of 6 kilometers, and the third one is shallower and is located at a depth of 2. So if we simply add the objective functions associated with individual point masses, the optimization does not do a good job, because in each case we are using 4 gravimeters corresponding to each point mass, and what we expect the optimization to do is to dedicate 4 gravimeters to each point mass. But as you can see here in panel A, there is no gravimeter on the characteristic circle associated with source number 1. And in panel B, you can see that these 2 point masses are getting 5 gravimeters, but the third one is getting only 2. So we change the objective function in this case and use the sum of the logarithm of objective functions associated with individual point masses. And as you can see in this case, the issue is addressed, and we get 4 gravimeters for each point mass. Therefore, we are going to continue with this objective function as the total objective function for the optimization. The next problem that we want to address is finding the minimum number of gravimeters for a network. So in this case, the target volume in which we have all our point masses is an area represented by this green crosses again. It is a rectangle, and the shallowest part of it is a cube, rectangular body. The shallowest point sources are at 2 kilometers, and the deepest ones are at 6 kilometers. So in order to find the minimum number of stations, what we do first is to find the information content for each one of these point masses. We find the information content that we expect from 4 gravimeters optimized only for one point source. But then we use these 4 gravimeters and optimize their location, considering all of the point masses. This way, we can calculate the information content that that corresponds to the new configuration. So in this case, in this figure, if you focus only on the blue curve on the top, we can see this new information content and the relation to the minimum number of stations much better. So we see that this curve represents how many point masses in the target volume are receiving enough information content, and by enough we have this 100% value on the y-axis in the figure. We see that as we increase the number of stations in the network one by one, the information content starts to increase, and as we increase the number of stations little by little, a larger number of point masses receive enough information content. So we continue this until all of the point masses in the target volume receive the minimum amount of information content, which for the blue curve is 4 stations. We can do the same thing considering a larger number of stations, and this way we can find the optimal number of gravimeters that we need in the network. This other figure shows the information content corresponding to the sources at the shallowest sources and the deepest sources, and we see as we increase the number of stations, the information content associated with the target point masses all increase. This method is, however, very time consuming because we are adding one gravimeter to the network at each time and running the inversion, the optimization again over and over. Instead of doing the optimization this way, we developed a second approach in which we start with 4 gravimeters in the beginning. These are the gravimeters that don't have any number in them in this figure. So as soon as we find the location of these gravimeters, we fix them, and in the next step of the optimization, we only add one more gravimeter to the network. And again, we can have these plots. So again, we have the number of stations on the x-axis, and on the vertical axis, we have the number of point masses that are receiving enough information content. So again, as we increase the number of stations, more of these point masses are covered by the network. And in this case, we should consider that the optimization involves only one gravimeter at each step. Therefore, the optimizations are super fast in this case. And again, we see that we see how the point masses are gaining more information in this scheme. So here is basically we see both of these approaches side by side, and we see that for the information content of associated with 4 gravimeters, both approaches they give the same result, which is 29 gravimeters. But we see that for a larger number of gravimeters, the approach 2 basically gives us a solution which involves a lesser number of gravimeters. In the end, we apply this to Mount Etna. So in this case, we have some constraints in the problem. First of all, we see the target volume again represented by these green crosses. In the side view, in the south-north cross section, you see how this target volume looks like. This we designed this target volume based on the information available on the sources of inflation in the past 30 years. And on the surface, we constrained the gravimeters to be located either on this summit road, represented by this line here, or on Forestaller Road, represented by this green line. And we fixed the locations of the iGraphs at SLN, Serra La Nova, and Montagnola here. And also we fixed the location of the AQG at this station up here. Following the approach that I explained in the previous slides, we could find that the optimal network in this case involves 13 MEMS gravimeters. And here you can see a closer view of the optimal network associated with this target volume at Mount Etna. In summary, we have developed analytical and numerical solutions for gravimetric network design. These the numerical approach can be applied to complex problems involving topography, and addresses the optimal location and optimal number of gravimeters necessary in a network, and can be used for rapid design for campaign measurements as well. So we have developed open source MATLAB codes for this purpose, and these codes are simple and can be converted, can be easily converted to other programming languages. And the method can also be applied to optimization of other geophysical monitoring networks, such as GPS networks and seismometers.